Consider a field extension K over F and an element alpha of K. Then we define F alpha to be the smallest subfield of K containing both F and alpha. Our objective is to understand this field. So we'll concentrate on the case where alpha is algebraic. Okay, and we'll use the substitution map. Recall, we had this map phi subscript alpha from ft to k. The substitution map was defined by phi alpha of ft is just f of alpha. This is a ring homomorphism from ft to k. And now look at the kernel of phi alpha. Kernel of phi alpha is an ideal in ft. Ft is a Euclidean domain and therefore a principal ideal domain. And so the kernel of phi alpha is generated by a single polynomial. Moreover, if we assume that this polynomial is monic, then it's going to be a uniquely determined polynomial. So this is equal to the ideal generated by Pt for a unique monic polynomial. Pt. Okay, and let's make another definition. Let's define f square brackets alpha just to be the image of phi alpha. Explicitly, this set is the set of all an alpha to the n plus a1 alpha plus a0, where a0 up to an are just elements of f and n is some non-negative integer. Because after all, it's just the image, it's the values, all possible values taken by polynomials evaluated at alpha. Now we have this homomorphism from ft phi alpha, and it goes from ft to k, but the image we have defined to be this subring f alpha of k. And the kernel is this prime ideal Pt. So phi alpha induces an isomorphism which we'll call phi alpha bar from ft mod Pt to f alpha. This is an isomorphism of rings. Now f alpha is a subring of k, and therefore f alpha is an integral domain, being a subring of an integral domain. Now remember that if you have a commutative ring and you go modulo an ideal and the quotient is an integral domain, then that ideal must be a prime ideal. Now in ft, the prime ideals are generated by irreducible polynomials, and in any principal ideal domain, in fact, the ideals generated by irreducible elements are actually maximal ideals. And so that means, well, the quotient of a ring by a prime ideal is an integral domain, whereas the quotient of a ring by a maximal ideal is a field. So we can conclude that ft mod pt, which is isomorphic to f alpha, is a field. Okay, now f round bracket alpha must contain f alpha because after all f square bracket alpha consists of elements of this form here, an alpha to the n plus dot 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 a1 alpha plus a0. Now a0, a1, all these are elements of f, and alpha is also an element of f round bracket alpha. So everything in here, this expression here, is the sum of products of elements of f round bracket alpha, and therefore this must be contained in f round bracket alpha. So what we see is that f alpha is contained in f round bracket alpha, but f alpha itself is a field. So f alpha is a field that contains both f and alpha. So therefore f alpha is equal to f round bracket alpha. Okay, so the field generated by alpha is the same as the values of all the polynomials evaluated at alpha. Let's look at an example. Let's take for our field extension the complex numbers over the rational numbers, and let's take alpha equals root 2. Okay, so firstly I claim that this polynomial here is called the irreducible polynomial of, where is it, PT. So this polynomial here is called the irreducible polynomial of alpha over f. Okay, so the irreducible polynomial, what is the irreducible polynomial of root 2 over q? Well, you can guess it is actually the polynomial t squared minus 2. Let's call this pt. Well, how do I prove it? So I need to show that if any polynomial vanishes at square root of 2, any polynomial with rational coefficients, then it is in fact in the ideal generated by t squared minus 2. So now suppose ft belongs to qt and f of square root 2 is 0. Now apply the division algorithm in the polynomial ring qt, Euclid's division algorithm. We have that ft is qt times t squared minus 2 plus rt, where rt is some polynomial of degree less than 2, the degree of t squared minus 2. And now let's substitute square root 2, and what you get is 0. We assume that f of square root 2 is 0 is now this t squared minus 2 also vanishes at t equals 0, and so this is r of root 2. So r is a polynomial of degree less than 2, which means that r is at plus b for some ab in q, and what we have is r of root 2 is 0. That means a root 2 plus b is 0. But this contradicts the fact that root 2 is an irrational number. And therefore, r has to be 0. Unless of course r is identically 0. That is a is 0 and b is 0. So then this implies that ft is in the ideal generated by t squared minus 2. So what we have is that q root 2, the field generated by the root 2 over the rational numbers, is isomorphic to qt mod t squared minus 2. And we also know that as a subset of the complex numbers, this can be written as, this is the same as q square brackets root 2, which can be written as a root 2 plus b, where a, b are rational numbers. This is because, you see, it's q square brackets root 2, but that's the set of all elements of this form. But if you take even powers of square root 2, they will just give you integers. And so every polynomial with rational coefficients, when you evaluate it at root 2, it will give you something of the form a root 2 plus b. And of course, anything of the form a root 2 plus b is a linear polynomial, so it's in f alpha. So here is a description of q root 2. You can think about it two ways. One, as a subset of complex numbers, it's all elements of the form a root 2 plus b, where a and b are rational. And the other is as a quotient of the polynomial ring, it's qt mod t squared minus 2. Now let's consider a slightly more general situation. So as before, we have a field extension k over f. But instead of one element, let's say we have r elements in K. Then we can define in a similar manner f round bracket alpha 1 alpha r to be the smallest subfield of K containing f and containing the elements alpha 1, alpha 2 up to alpha r. Now you can again define a substitution map, but from a multivariate polynomial ring. So define a substitution map. We'll call it phi subscript alpha 1 alpha r. It's going to be a ring homomorphism from f with polynomial ring with r variables into K. And what it's going to do is phi alpha 1 alpha r, as you can guess, evaluated at t1 to tr, will just be the value of phi at alpha 1 alpha r. So you substitute for ti the value alpha I. Now I claim that in this case also the field is just given by the values of polynomials f alpha 1 alpha r is equal to, so let's just define this. We'll define f square brackets alpha 1 alpha r as the image of phi alpha 1 alpha r, which is a subring of K. So this is equal to f alpha 1 alpha r. The proof of this just goes by, alpha r, not r alpha. The proof of this goes by induction on R. So the base case R equals 1, we've already proved over here. Okay, and so now let's look at f alpha 1 alpha r. So there's a very simple trick to this. It is just to realize that this is, so to change this whole situation as f alpha 1 alpha r minus 1 alpha r, that this is just the smallest subfield of K containing this field f alpha 1 alpha r minus 1 and alpha r. That turns out to be the same as the smallest subfield of K containing all the elements alpha 1 up to alpha r. But by induction hypothesis, this here is f alpha 1 alpha r minus 1, and of course applying the base case, this is the same as polynomials in alpha r. So this is a field and this whole thing is in fact a field, but this is the same as f alpha 1 up to alpha r. So we also have the multivariate case where the field generated by R elements is given by the values of polynomials. Of course, here we need to assume that all these elements are algebraic, otherwise this doesn't work, right? Because at each stage again we're using the fact that alpha is algebraic. What happens when alpha is not algebraic? Okay, so let's just look at that case. Suppose we have alpha in K over F, and suppose alpha is transcendental. Then we know by definition of transcendence that phi alpha from Ft to K is injective. And in fact the image, suppose we define the image to again be phi alpha, then this is an isomorphism. And so taking fraction fields Ft is actually isomorphic to F alpha. So this suggests an alternate definition of transcendence, which is that alpha is transcendental over F if and only if F alpha is isomorphic to Ft. The smallest field in K containing F and alpha is isomorphic to the field of rational functions with coefficients in F. So we can use this definition to sort of directly jump to the multivariate case, and I'll give you a definition here for the generalization of transcendence for n different elements. Alpha 1, alpha 2, alpha r in K over F are said to be algebraically independent. If the smallest field containing alpha 1, alpha r is isomorphic to the field of rational functions in R variables, which is equivalent to saying that the polynomials in alpha 1 up to alpha r are isomorphic to polynomials in T1. So we're saying that there are no algebraic relations between the elements alpha 1, alpha 2 and alpha r over F. So it's again this algebraic, just as with transcendence, algebraic independence is a difficult problem. It is conjectured but not proved that E and pi are algebraically independent. But it's something that's not known. It's a big open problem.